I'm very happy that we're starting this new experiment with expert briefings prior to the PyData Global Conference. And thank you, Thomas, for being the first in the 5 that we are running this week. So Thomas has been a long time open source member, one of the core developers on the PyMC3 probabilistic programming framework, which alongside Stan is one of the 2 most popular of their kind on the planet. Thomas is going to give us a state of the art for probabilistic programming in general, and then open the floor to questions. And so Thomas is well known in the PyData world and then the wider academic world. So Thomas, over to you. We're recording this call. We can go on for an hour or less as needs be. Thomas, please take the floor.
Well, thank you so much. Thanks everybody for joining. I'm very excited to be here and talk about my favorite topic, probabilistic programming and PyMC. I just have a couple of slides. Really, the idea of this format is that it's interactive. So there will be maybe 10-15 minutes of slides where I think where we are today and where we're headed, and then open the floor to questions and discussions. So yeah, really looking forward to that and hearing from you. So I'm Thomas. I am most recently the CEO and founder of PyMC Labs, our amazing Bayesian consultancy. We basically just help customers build and solve the most advanced data science problems they have using Bayesian modeling and probabilistic programming. And I couldn't be more proud of the team that we have assembled. There's actually quite a couple of more people now than that are listed here, but we all come from the PyMC core developer team, so we're the inventors of PyMC. And between us, we have decades of experience in this type of Bayesian modeling, right? We wrote it and we just love using it. So it was very natural to basically jump in and start this consultancy. We work with clients from startups to Fortune 500 companies and have a team of diverse backgrounds. So probably most of you will be familiar, but maybe some of you are still like, well, what is this Bayesian probabilistic programming thing I keep hearing about? So I just want to give like a very, very high level overview of what I think really is the main reason for why you should be interested in this and what sets it apart really from other approaches, because I think it is very unique and gives you a lot of power and freedom. So very high level, for me, the reason to use it is because it gives me great flexibility and allows me to really express my creativity in solving these problems, and is really empowering. And I think you'll find that when you start using it, that you just become a different view of the world, basically, and what you can, and the type of problems that you can solve. And I'd like to illustrate this with this small comparison here, where we have Playmobil. So in Germany, when you grew up, there were Playmobil kids and there were Lego kids. And basically, Playmobil is, you get a prepackaged toy, right? Here's the ambulance, and you can only play with it in the way that it was designed to do, right? You can't turn this into a rocket ship. It's an ambulance, and that's the only thing you can do with it. But I mean, it's nice, right? So it is like very shiny and prepackaged. You don't have to do anything to get it out of the box and immediately can start playing. So that's cool, right? But it's not as flexible. And this is what I would label more traditional frequentist statistics and most machine learning approaches, where you have the pre-specified algorithm, right? And it does what it's doing, and you can't really change it. Now contrast that with Lego, right? Which, I mean, nowadays the two have become more similar, but back in the day, really all you got was just a whole bunch of individual parts, right? And from that, you could build a particular toy, but you could all build all kinds of other things. And I always thought that this freedom was really empowering, right? So if I wanted an ambulance, I could build an ambulance, but if I wanted a rocket ship, I could use those parts and some other parts to build that rocket ship. And yeah, so that I think is really empowering, and how I like to think of Bayesian modeling, because it really is giving you those basic building blocks in terms of probability distributions and allows you to assemble them in all kinds of different ways in order to solve not every prediction problem out there, but the very particular problem that you have in your data science task. And the other really cool thing about it is what I like to call the democratization of statistics, where back in the day, you really needed a whole lot of math, right? If you wanted to build your own model, you had to derive, say, your own estimators, right? You couldn't just say like, oh, that's the model I want, let me just like fit it. But with probabilistic programming, we actually can express our models in computer code. And with PyMC, you can do that in Python. And that is part of that. What makes it so powerful for me is not only can I build these flexible models, but I can also assemble them in a few lines of Python code. And then finally, the fitting of that is actually automatic. So to summarize the idea, we have data, and then we have a custom Bayesian model. We don't have a black box. We don't have a t-test. And then the output of that are probabilities. So we can reason about things in a probabilistic sense, meaning we can quantify an uncertainty and our risk that we're taking on. So as I said, we can tailor a model to a specific problem. We can also incorporate expert domain knowledge, right? Anything we know about the structure of the problem ahead of time, or maybe about certain parameters that we think are going to be in a certain domain. We can incorporate that. And that in the business setting is also incredibly powerful because it allows you to talk to your stakeholders, right? And let's say with a black box machine algorithm, essentially what you have to do is come in and say, well, maybe people in this company already have decades of experience solving this problem. We're just going to throw all of that out the window, and we're going to just train a classifier on data, and that's all there is to it, right? And that's going to replace everything. Here we can actually talk to these people and say, okay, well, what have you learned? What is your insight? And incorporate that to the model and get the best of both worlds in this way. And that usually goes way better if integrating this. And of course, coupled with the transparency. And as I said, probabilistic programming allows you to do that in computer code and fit those models automatically. So that leads to a really fast iteration cycle and building custom solutions quickly. So I would go on the record and saying, I think it's the easiest and most powerful framework for statistical modeling currently out there. Okay, so that's basically the intro. I'm going to skip this here. But now you might be wondering, well, if it's so amazing, why is not everyone using it? That's a good question. I mean, the main reason is I still think it's not as well known as it should be. So I think more people should be using it because you can use it today to solve really tricky industry scale problems, and we do, right? That's thousands of people, thousands of papers have cited PyMC. Many companies are using it, and it's not a toy, right? It is an industry scale application tool. But I still think that there's a lot to be desired, and that's what I'd like to talk about next. And one of the key things that we keep hearing is that probabilistic programming is slow. And that is true to a certain extent. It's a little bit more nuanced. So first of all, it used to be much truer than it is today. So we used to be able, so these early systems, they didn't really scale well in terms of the model complexity, right? So you could build regression model, right? And then automatically fit that, things like Winbugs or JAGs. You couldn't really use a lot of data or very complicated models. These days, I would say we scale to like medium-sized complexity in terms of model and medium-sized data sets. More concretely, what I mean with that is we have fit models with 40 to 50,000 parameters in under half an hour at Quantopian, for example. And we have also ran it on models with 1 million data points. And that works, right? So it scales that far, which is not nothing, right? You can solve all kinds of problems with that. And especially a lot of times Bayesian modeling is being used in the domain where you don't have as much data, right? That's where things like priors and expert knowledge become more relevant, because if you don't have a lot of information, you need to gather information from other sources. But if you do, well, of course, you might still want to use Bayesian models and more complicated models. But yeah, currently the scaling beyond that is still an issue. And I mean, certainly there's many data sets with more than 1 million rows and models where you want to fit more than 100,000 parameters. So I think that is really the future. And I think there's a really good story for it where, well, if you have that much data, the model that you can't fit is also going to be, is allowed to be much more complex than not, right? If you have more information, you can infer more patterns from the data and you can include those into your model. So with big data, you can build more complex models. But currently, the tooling is still not quite there, but that's what we're about to change. Yeah, so this is what I said. We can scale, especially the NUTS algorithm or Hamiltonian Monte Carlo is what essentially allowed the second generation. So the first generation I would call WinBugs and JAGs, second generation STAN and PyMC 3, which have adopted these gradient-based samplers, NUTS and Hamiltonian Monte Carlo, to make it scale to this medium size. And but I think we need to venture into this third domain. But the other take also is, and we see this all the time, so customers come to us and they say like, oh, our model takes 6 to 7 hours to run. Can you help us? And we usually get it down to 30, sometimes even less than 10 minutes. But only part of that is really working on the core speed of the model. A lot of times when you have computational problems, there's really often a problem with your model. So that is the first thing that should be addressed. And that is where we get insane speedups, just because the sampler is working much better if you have a model that's easy to sample from. So this is known as the Folk theorem of statistical computing, expressed by Gallon. And yeah, like this couldn't be more true. Like almost every model that we work with, we find some issues that we fix. And then the whole thing just works much better. There are no divergences, sampling is fast. But it's actually quite difficult. So that is why people come to us, is because they can solve that on their own. And this is what I personally started calling the dark arts of Bayesian modeling, which are model reparameterizations. And this is an advanced topic where essentially if you write a model, right, let's say it's a hierarchical model, there's not just a single way to write this model. There are at least 2 ways, often there are many more ways. And even though the model is conceptually the same, the 2 models, just under a different parameterization, sample completely different. So they can be much faster sampling or have fewer divergences by just applying a simple mathematical formulation. And what's even more difficult is that it's not really clear which parameterization even is available, right? So if it's a hierarchical model, there's a non-centered and a centered parameterization. First of all, you have to know about that. There are many other ones which you have to know about, right? There's no cookbook, or that process is not automated. And it's also not clear which one is the best. Sometimes the centered parameterization is best, sometimes non-centered parameterization is best. It does not only depend on the data, also depends on the does not only depend on the model, but also depends on the data. So it's even trickier. So yeah, this is quite challenging and something where you need experts like us to do that. But ultimately, I mean, we do want to make that more automatic. So PyMC 4.0 is going to be the future and address all of those problems, or at least lay the groundwork to really solving those problems. A little bit of history, because we did quite a few renames to clear this up. So PyMC 3 is the software that has always been around, and it was based on Theano, which is the core graph computation library that allows you to express computations as graph representation and then compile those to C. Then, so Theano was the predecessor of PyTorch and TensorFlow and all these other packages. And then they discontinued. Then we started to experiment with a prototype called PyMC 4, which was based on TensorFlow, TensorFlow probability, but pretty quickly we abandoned this because we found that TensorFlow was not the right fit. And Theano actually was pretty much perfect for what we wanted to do with it. So what we did was fork it to something which is now called Theano PyMC. And the current version of PyMC 3 rests on our own forked Theano version. And while forking it and fixing some issues with the code base, we found that actually Theano is an amazing library. It just was a little bit stuck in the past and a bit crusty. So we went in and fixed many issues there and renamed the library by rewriting it to Sara. So this is the new library, and Theano is the predecessor. So there's an extension of that, but it's actually quite a substantial rewrite in many ways. And PyMC 4.0, so we're renaming PyMC 3 back to PyMC, right? And then we just use consecutive version numbers, so there won't be a PyMC 4 or PyMC 5, there will be a PyMC 4.0, PyMC 4.1, right? And just like like a sane person would do it, right? So we're going back to to that. And that will be based on Sara, and the beta is going to come out in, I think, maybe 2 weeks. So we're very, very close. And what's exciting about it is that, well, there are many cool new features in it, but the two main ones that are most visible are new computational backends. So you can not only compile to C, but you can also compile to Number, which is an LLVM compiler by Anaconda. And that gives, it's really nice speed up in some scenarios, not in all, and still something that we're actively working on, and also JAX. And for anything that has like large matrix multiplications, JAX is actually really powerful. And if there's other libraries, we can also target those quite easily. So Sara is basically this middle layer, which does the graph representation, and that can compile to different backends that are then fast. So what's new here? Well, we try to address all these issues that I just mentioned that are holding probabilistic programming back. So we get better scalability due to the JAX and Number support. And through JAX, for example, we also get GPU support natively, right? And TPU support even. And in like some early experiments, we've seen 10x speedups on a logistic regression model using this. Sometimes we've seen even higher speedups. So this allows us to really put more oomph behind the raw sampling. Another thing which we started doing is before our samplers were written in Python, and only the model block probability was written in basically Theano or Sara, and was then compiled. So the Python sampler was calling into the C speed run model lock probability. So of course that's still slow, right? There's the overhead that you eat, and there's certain optimizations you can't do. So now that we write the samplers in our Sara themselves, the whole model is basically its own computational graph, and we can do interesting optimizations on that graph level, and then compile the sampler and the model block probability to either JAX or Number. In the case of JAX, for example, and if you want to run it on GPU, then the sampling and the model lock probability are running on the GPU. So it's just one program and you set it off, and that would become much, much faster than just the 10x speed up. So really excited about that. That one will take a little bit longer. And the other thing, what this allows us now to do is these automatic graph rewrites. So there's some simple ones, right? So if you just have the log of an x, you can simplify that to x. That's going to be more numerically stable and faster. So we can discover those easily now and optimize them away. And there's more and more that we're adding. But we can also do that more in a statistical way. So if you have a normal distribution centered on 0 and 1, and you multiply that with a value and add a value, well, you can rewrite that to just be normal distribution centered around mean A, standard deviation B. So, and again, like sometimes this parameterization will be better, sometimes this other parameterization will be better. And we can automatically generate those. So that's also something that basically then allows you to automate this dark art process by just encoding all these parameterizations that you can do into our rewriting engine. And then we can just generate different types of parameterization for the model, and that the user doesn't have to do that. And we can do much more, like marginalization. If you have discrete parameters, these nice Hamiltonian samplers do not work. So we can do that automatically. And then another big thing, of course, is just better teaching. So I think these tools and concepts can be taught much more intuitively and efficiently. And we're now creating an online course in intuitive Bayesian modeling that you can check out on my homepage, which is going to be an online course where we teach you how to use these tools most effectively. Here's some references. Yeah, check out our sweet Bayesian consultancy if you have data science problems. My blog, where I have all kinds of blog posts and tutorials on various PyMC tricks. The website for PyMC, Twitter, or you can email me. And yeah, so with that, I'd like to open up the floor to questions, discussions. Here are some discussion points. Maybe first we start with questions, but also if you'd have thoughts to share on like what have your experiences been? I'm really curious to hear. Have you already used PPLs in practice? How's that been successful? What stumbling blocks did you encounter while doing that? And which probabilistic programming language are you using and why? So so maybe we'll just open it up and we'll, I don't know if you want to moderate, Ian.
For sure. So first of all, Thomas, thank you very much. You're bang on time. And that was a nice, clear briefing. So thank you very much. That's great. Everyone else, it'll be good if you could say thank you to Thomas by going to the chat window and saying thanks or something along those lines there, or waving. Yeah, exactly. Waving or saying thanks in the chat window, whichever one works for you. But that was very good. And to ask questions, I would propose either unmuting yourself and then saying, hey, Thomas, and asking the question, or in the chat window, making a clear question there and typing it out so that Thomas can field it. Either is good. I'm going to try and keep out of the way of this. So either speak out loud with your question or type it into the chat window. Either's good, and I'll just step back. Thank you, Thomas.
Thank you. Yeah, thanks all for the positive vibes. I appreciate it. PPL stands for Probabilistic Programming Language. That's an easy one to field. But yeah, also feel free to unmute yourself and share your own experiences. So yeah, like who here has used probabilistic programming successfully, and what has your experience been?
So there's a question at the end of the chat there for you, Thomas.
Okay. Do you recommend any ways of introducing PPLs and Bayesian statistics to the wider community? Find that there's a steep learning curve. Yes, I think you're right on the money there. That is still the biggest problem holding it back, is that things like scikit-learn, right, is amazing. You just import a random forest, you run it, and then it does something quite sensible most of the time, right? These are very robust, and if you have a problem that fits into that mold, it's going to do the right thing. And what's cool is you don't even have to really understand what a random forest really does, right? It will just, most of the time, it will just work. If you do understand it, that's helpful, right? Then you know, like, oh, about the tree depth and all kinds of other hyperparameters that you might want to tune. But really, it's pretty easy to get going with that and get good results. Probabilistic programming, you have to know more. You have to know probability distributions. You have to know some core of conditional probability, right? And how it all fits together. Then you have to have just this practical experience of doing it. So I've definitely been guilty of this in overstating maybe how simple it is, right? I mean, because I think, yes, you can do very powerful things, and the probabilistic programming makes that simpler, but is it really easy? Well, not really, right? If you actually then go down to sit and build your model, you maybe are able to write it down, But then you're like, well, which prior should I use? Like, why? How do I find that out? Then you get divergences with like really cryptic error messages. What is that about? So yeah, those are things that the course is trying to help you with, like what type of priors and just better documentation. But yeah, I think there's a lot to be done here. I'm just talking about a question. Yeah, so yeah, I think it's just the efforts that we are undertaking in terms of making it more intuitive, because I think actually a lot of the teaching materials are quite bad. So like one of the Bibles, I guess, right, is what is that most famous Gelman book, Bayesian Data Analysis, BDA, and that starts out just very theoretical, right? And it's not hands-on at all. So if that's the first book that you pick up, it's quite easy to be frustrated. And I have had those frustrations in learning it myself, where I found like, oh man, once I like finally got a concept, I'm like, okay, well, this is actually quite straightforward. Why hasn't anyone like explained this to me in normal terms? And that's what we're doing with that course. And that's what I'm trying to do in my blog. And I think there is this other way to like ramp people up in being much more hands-on and working with it. Of course, not by now, they're also much better books. Statistical rethinking is really good. There's a book for specifically targeted on PyMC. Most of these books also, like statistical rethinking, we have ported to PyMC, so you can read the book and still use the PyMC code examples with like links on the website. So yeah, that's what I would say. There's a raised hand. I can't see the name, but you have your video on.
Hi, Thomas.
Hey.
Thank you for the talk.
Oh, thank you.
And thank you for all your efforts in PyMC in general. I just mentioned that PyMC is my go-to tool. Oh, sorry. So I should mention I'm a data scientist. I've been doing analysis for about over 15 years now. And PyMC 3 is my go-to tool, especially when I have to deal with something something that I can't solve analytically. And so I use it on a professional level, not day to day, but at the random chance in which I need to solve something. I can give like a concrete example, for example. So if you're, so just the simplest thing one can imagine, just beta distributions. Let's say you have a model accuracy, but you can't sample all the data. You have a small sample. So I deal with a small sample statistics. And so, you know, a beta distribution represents the accuracy of the model. But then you have more challenging questions like, well, let's say I have two models, A and B. Is one better than the other? And all I have is a small sample. And I looked online and I see there's no analytical thing that I can just pen and paper write it down. And correct me if I'm wrong about that. And so I figured, well, PyMC, I can just write down the better distributions of each and just sample like differences between them and create a metric. And that's kind of like how I solve for that. Please correct me if there's an analytical solution that I'm missing, and I can do it. But otherwise, I'm looking forward towards your course, by the way.
Oh, thank you.
I can learn how to use it more effectively. Yeah.
And if you want to share, like, what's the specific problem? Like, what's the domain that you're working
I
on?
work in healthcare.
Okay. And what's
so
the
I'm looking
data?
at the,
yeah.
I work on a feature called Symptom Checker. You put in your symptoms, and it will tell you what level of emergency should you deal with it. Is it just go to the pharmacy, or God forbid, go to the hospital? So we have our AI give, you know, what it thinks the truth is, and then I compare that versus what a clinician says. So we have various metrics of accuracy. One, for example, is safety. How safe is it? Meaning that if the clinician says the outcome should be you should speak to a GP within 24 hours, and the AI, let's say, says something like, oh, this is something that you can take care at home on your own, then that would be considered not safe. So I want to quantify how safe is the product. And so I have model A that has some accuracy level, and then I have model B that has a different accuracy level. But because the ground truth is very expensive. We have to pay clinicians to go over what's called a vignette and actually give the ground truth. I cannot I cannot annotate all my data, but I have a small sample. And so that sample represents the model at large. Does that make sense?
Yeah, it really does. That's such an interesting application for it. And why did you use PyMC and not like machine learning, not scikit-learn or something like that?
Oh, because I don't need to use machine learning. It's very simplistic. I just have, you know, 2 columns of data. I have the ground truth, and I have you know, the ground truth from the clinicians, and then I have from the AI. And I'm just doing an analysis. I'm not doing like machine learning to update our models. I'm just reporting as an on the, you know, reporting as an analyst, like, okay, the performance of the model. And I want to know, again, we're dealing with small sample statistics. Like, I want to know the credibility of what the accuracy of the model actually is. And if I have 2 models, then that becomes, you know, more parameters. And then I want to compare between the 2. And I can't do that analytically. And so that's why I just chuck everything through PyMC3, and then I can do that minus sign between the 2 samples, and then I have distribution of what the difference would be between the 2 models.
Yeah. So essentially, it's a hypothesis test between 2 different models that you have, right?
I should have started my answer with that. Yes, that would have been much more clear. Hypothesis.
Yeah, no. I mean, yeah. Yeah, that's interesting. And I mean, that's definitely a totally valid application of PyMC. Like, so one thing you could look at is the best Bayesian estimation supersedes the t-test.
Yes, that's exactly.
Paper by Krushki.
Yeah.
Oh, that's what you're using. Perfect. Yeah.
I adhere by Krushki's philosophies. Yes.
Yeah. Nice. That's another great book, by the way. But yeah, it sounds like definitely the right type of tool. And I mean, one thing definitely that shines through is that you really need good uncertainty quantification, right? So it's always interesting to hear about these problems because, like, yeah, we basically by now broken it down to these types of things that allow you to identify whether your problem is well suited for probabilistic programming. And you mentioned a couple of those, right? You have small data set size, so probably classified that you can get off the ground. So it's not a simple prediction problem. You want to gain insight. Uncertainty plays a big role, and it's about real world decision making, right? So and for me, like, that point is always a little bit funny because, well, if you're not doing real world decision making, why even trying to solve that problem in the first place? And I mean, I guess like, let's say Amazon or something, right? If you don't make the perfect recommendation, it's not the end of the world, right? The person maybe just doesn't buy as much. But in this case, right, whether someone like goes to the ER on time or not is like really critical. So there you want to be really conscious of how sure am I in that recommendation, right? And if you're unsure, maybe you want to have a second system and go to an expert and say, well, I don't know in this case. So yeah, that is one downside of many of these black box machine learning algorithms is they can't convey what they have learned, and also how sure or unsure they are on the answer, right? They don't really have a way of saying, I don't know.
Yeah, that's an excellent point. And what you talked about, the safety of the patient, but also from the practical sides of logistics, like if I report that the model doesn't perform as bad, the model, you know, the new model doesn't perform as well as the first model, then that will require a lot of prioritization of resources like engineering efforts and more data scientists. So I like your point about real life decision making in that sense.
Yeah. And another thing that you might want to look into is model comparison. Probably you've already come across this, but what you said about like comparing 2 types of models, there are like certain scores that you can use, like leave one out cross-validation is a concept that's also in Bayesian modeling. And we have those in RVs, which is the statistical library that accommodates PyMC. So that's something to look into. But yeah, thank you so much for sharing that. That was really interesting. Exactly the type of discussion that I was hoping we could engage in here. So next, I'm going to take a question here from the chat by Palini. I have a question. I always had the feeling that the flexibility of using a Bayesian approach also comes with a cost of the extra time needed to get some good results. extra time compared with frequentist approaches? Assuming this is true, do you have some layman selling points to justify this extra time with business stakeholders and get their buy-in? Yes, so I wholeheartedly agree with the first premise of the question that the flexibility does come at a cost, at the cost of greater time to build a model. And I guess that point is easier demonstrated if we compare it to machine learning, right? Because machine learning, as I said, is like this super quick thing. You just import it, you run it, you get results, perfect. But then, of course, if you have more things that you want your model to do, like you have certain structures in your data, like hierarchical nested data, then basically it becomes impossible, right? Versus Bayesian modeling, you can do that, but it takes much longer to build that model. The other comparison that I like to use is, well, no, let's stick to the Lego one, right? I mean, yeah, building your own rocket ship in Lego bricks takes more time. But you get exactly the type of thing. So that cost, I don't think we'll get rid of, mainly because it is in the nature of the approach. So if you want something hand-tailored, right, you have to hand-tailor it. There's just no way around it. And there have been like ideas of like an auto statistician, right, where you just have a model that's just going to fit everything. And there are some interesting approaches there, but I think it misses the point where we want to use Bayesian modeling for those cases where we have that knowledge and we want to fit a very particular mold, and that just takes time and exploration. But that is not wasted time, right? Because not only do you get a better model, but also you learn something about your problem. So by building this model, it's really interesting process, and I think you really have to go through it in order to fully appreciate it. As a lot of the assumptions that you had coming into this, you realize were wrong, right? So, and you realize that through two ways. One is, for the first time, you're really now forced to write down exactly what you think the structure in this data set is, right? So for the first time, you're like, oh, well, does this thing connect to this thing? And is there a hierarchy here? And what is the likelihood function? So now you're forced to write that down, and that helps you to clarify your own thinking. And then, well, once it's written down, you can communicate that to other people. So that's good. But also then when it comes in touch with the data, right? Like that quote, everyone has a plan until they get punched in the face. So every model is like perfect until it gets punched in the face by your data set. And then you're like, oh, well, I guess this wasn't quite the case. And then you revise, right? And then you learn something about the data. And maybe at the end of the day, you throw away the model, right? Because now you really understood what it is. And maybe it's something very simple that you can do, but the path is what got you there. So then the second part of the question goes about frequentist modeling, which she says is often faster to run because it's off the shelf. So that is a little bit more nuanced. I understand the premise, and I agree with it to some extent that there is very much also this technique mentality, right? Where instead of scikit-learn, you have stats models, right? So you import your t-test or your OLS and you run it, and it takes a couple of seconds, and then you get your output summary and you're done. So that seemingly is as simple as machine learning. And in a way it is, but there it's a little bit more tricky, because by using these off-the-shelf statistical tests, you can shoot yourself into the foot really easily. So for example, maybe your data isn't normal because you have outliers, or maybe it's count data, right? In that case, you violated the assumptions of your test. If you use a t-test, for example, right, which has a normality assumption, and then the results that you get are going to be biased. So, or maybe the algorithm hasn't even converged correctly yet, right? You have some like crazy complex model that's overfitting like crazy, but you actually don't know. You still get answers, but it doesn't really tell you about the quality of the answers. So it's very easy to think that you actually have a good model while you actually don't. And part of what makes Bayesian modeling hard is that it's really shouting loudly at you when you do something wrong. And that's actually a great benefit, because that is what, coupled with this Folk theorem, right, is when your sampler doesn't converge, right, you know that you have a bad model most of the time. So, and you want to know whether you have a bad model, right? You don't want to fit a bad model that doesn't fit well and have a better sampler. It's telling you that you need to improve your model, and that takes time. So I guess one way, so yeah, I would say, so that is usually what I say then to stakeholders, that frequentist statistics is more inflexible and gives biased results. We see this, for example, with A/B tests all the time, right? So people are like, oh, I have an A/B test. Let me just run a simple t-test. Well, first of all, it's count data. Second of all, what they often do is like, oh, I ran the A/B test, my experiment for a day. P-value is not below 0.05. 2 days, still not below 0.05. And then after a week, like, oh, now it's below 0.05. Perfect, that's what I wanted. So now I'm going to go live with this version. But this repeated testing is something that you just cannot do in frequentist statistics, right? Because frequentist statistics is very backwards in its philosophy. So it's not wrong, but it's just wrong for most of the questions that you actually want answers to. So p-values are famously misunderstood. And I can't even explain here what a p-value is, because it just is so weird that most people would be like, just like, what did you say? And if you ask scientists, for example, what a p-value is, they describe to you what a Bayesian probability is, the Bayesian interpretation of it, just because it's so weird. So by now, the replication crisis and all of that are really good indicators that frequentist statistics is just does not provide the answers that we usually want, and is biased in all these different ways. And this apparent simplicity is, I think, sort of a false benefit, because you actually don't get the benefits, you just get the speed. I hope.
Thank you, super useful. Thanks.
Glad that was useful.
It is worth mentioning that the frequentist, and I'm on your side of the discussion, but it is worth always reminding that frequentist and Bayesian approaches lead to the same answer when n is very high, and then you really want Bayesian when you're dealing with smaller sample size. That plus the benefit of Bayesian you can use priors.
Right.
So I think those are two arguments that one should have in mind.
Yeah. I'm not sure actually it has to be true that with lots of data you get the same answers, but nonetheless, so the added flexibility of Bayesian modeling, I think that is actually the best selling point. Is you can build models like hierarchical models. Frequentists have that with mixed effect models, but there are also some critical elements missing there. So they have some approximations of the real thing, a hierarchical model, but yeah, it has all kinds of issues. So the flexibility, the fact that you get better uncertainty quantification, so the concept of uncertainty is just much more grounded than in frequentist, where you have this weird sampling approach. And well, there's one example, right, where you have a confidence interval, but then the confidence interval is actually completely outside the domain of what is even possible in terms of values. It's not even, does not even include any of the data points that you have observed. So there are like some weird cases. And it's not that the confidence interval is wrong, right? It's just that we all understand it wrong. So yeah.
Yeah, those are excellent points. Thanks for that.
Yeah, thank you. Okay, what else do we have? I often find, so this is from Chris, I often find creating a data generating function, creating by toy examples, a difficult process. Do you have any suggestion for getting better at this, or any plans to include in the course? Interesting. So yeah, this is something that I haven't really mentioned as much, is that these Bayesian models are inherently generative. So often what you try to do is you have a generative process in your head and you map that to the model. So you have that generative process of how my data was generated has some hidden causes. And I have an idea of how these hidden causes gave rise to the data that I observed. So now that I And then I built a Bayesian model to essentially map that generative process, right? So that generative process has these hidden causes, my parameters and priors on them. And then through some other distributions and some computations, it then generates the data. And then, of course, in reality, I only observe the data. And then one reason backwards from, given that I have observed this data, what are the most likely hidden causes that have generated it? And that's what Bayesian statistics is doing. And that's what Bayes formula is doing, right? It's just inverting this. Back in the day, it also used to be called inverse probability because of this property. So I would even say that if you have, so the question is maybe, okay, so I'm going to interpret this in a particular way, and maybe that's the wrong way, but I would go as far as saying that if you can't write down the generative process easily, you don't really understand your problem well enough. So I think that's what I would invest in, is in thinking more clearly of like, what is the almost like the physical process that generated it, right? So one example that I like to use is that a COVID reproduction model that we worked on with Kevin Systrom, of all people, the founder of Instagram. There was a website, rt.live. It's not live anymore, but we worked on this model in PyMC with him. And this was like, for me, the epitome of generative modeling, because you wanted to estimate on a certain day what was the reproduction rate, the effective reproduction rate, meaning one person infected 2 other people, 3 other people, 1 other person, 0.5 per people, right? So that was changing all the time. So that was the hidden cause. But to go from that hidden cause, there's many things until you actually observe the data. The data being that how many people got a positive test on that day. So in between, you have, well, person A affects 2 other people, then those 2 other people first have an incubation period. Then they have a certain probability distribution of developing symptoms. And then they have a certain delay until they start actually get a test once they have symptoms, right? And then there's the testing frequency. So can they even get a test, right? Because that changed over time. So all these things, right? So from the one person infecting to another down to them coming up in the final statistic, the data set that we have, is like a long causal chain of individual steps, and there's like delays in there too, right? So usually that number only gives you about like the people that got infected 2 weeks ago, right? So there's this whole delay thing. And we mapped that whole process to PyMC. It wasn't easy, but it requires us to really like dig in and think deeply about this and understand the domain. So there's no shortcut to that, I would say. But certainly the course that we have will go through that whole logic and how, once you understand it, how you pour that into a model and how you map that. So that still requires domain expertise, or at least talking to a domain expert to get that download. But once you have that, the course will tell you how to do that. And one good exercise that we also often go through is to test is to just build the model without any data and just generate data. And then you see, okay, does that generate the types of patterns that I expect from my data? It's called a prior predictive check. So I hope that that was useful and I understood your question correctly, Chris. Sean Law, oh yeah, I know you from Twitter. Is there a good resource reference that you can recommend for seeing practical examples for where PyMC generally works best? So actually, so there's a whole bunch here. This is the PyMC website, and then also with code. And then, yeah, so there are certain case studies. Actually on the, and then here in the slide deck, I also have some examples. So this is the COVID-19 example that I talked about. Then we have a blog post out on our PyMCLabs.io about how we worked with HelloFresh on the market mix model. So this is a model where you have all kinds of different marketing channels, Google ads, Facebook ads, TV ads, radio, right, everything. And then you only observe a single thing, which is how many customers have you acquired. and you want to know how much did each channel contribute to this. So you're trying to remap, undo this many-to-one mapping. And PyMC is a model, and like that is used in production. So this is a very famous model. But I agree that actually there's not a whole bunch of good success stories. So by now we know quite a few of those, but yeah, not everything we have written up yet. So here's another slide deck also with some examples, and one I particularly like. Civics, for example, we also worked with them. So civics.com, I think, they have a political sentiment. So how do people think about the coronavirus outbreak? So this is a Bayesian model also that's running production every day. We help them speed it up. Yeah, so those are some examples, but I agree, there could be more. How compare Stan and PyMC? Doesn't even make sense to compare them. I mean, yeah, they both try and do the same thing. So Stan and PyMC came out roughly at the same time, Stan a little bit earlier, and they were both the first ones to work with the NUT sampler, which really changed the game. And they and we actually copied a lot from Stan. So a lot of the because they are not only the people writing software, but they're also often the people like Gelman really pushing the field forward. So we are indebted to them in many ways because they gave us a lot of tips and help early on how to do this. And yeah, a lot of things are just copied from them. They chose a little bit quite different approach technically, where they said, okay, well, we're going to write our own C++ backend almost. And we just decided to use Theano. And I think that was a good choice for us, just because of the simplicity. So the whole PyMC code base is much more approachable, much easily hackable. And now actually, I think there's many things that we can do with these whole high-level symbolic rewrites, right? Because we have access to the whole graph of these computations, like here's a normal random variable and you multiply that with another one. So what happens here? And we can rewrite this. So that allows us to do many things that are really hard for them to do. So I think that's a good thing. And then also now we have the ability, right, to switch out these computational backends, which is also going to be difficult for them because they're sort of married to C++. So I would say those are some of the differences. Personally, I think my biased opinion as one of the authors is that the PyMC model specification API is nicer. I also think objectively that's the case. In Stan, you have to have define like a random variable sometimes in 3 places, right? One is for the transform, and then how you want to use it. But they also have some really nice features that we don't. So loops, for example, you can write some time series models much nicer in Stan. Although in PyMC 4.0, we will be able to have the same way of doing that. So, but yeah, so Stan is amazing, and they have a great community. But yeah, I would still say if you actually are a Python user, I hope PyMC gives you the better experience, and if not, that's something that we want to fix. 100 data points, yeah, exactly. So that's where in DNA sequencing.
No, it wasn't sequencing. It was DNA yield. So measuring the concentration based on reagents.
Yeah.
Sequencing is a much more complicated problem.
Yeah, and that's where you have tons of data too. Yeah. Here's one, Raphael. It is possible to use empirical distributions along with PyMC. Sometimes using something like bootstrapping for approximating the distribution is more convenient than having a specific one. So there is a thing where you can approximate a distribution from samples. So basically histogram. And that is even here somewhere. I have too many windows on top of it to really see. Well, I probably won't be able to find that in time, but there's an example here where you can do that. And however, I wouldn't recommend it. So most likely there is a better solution, I would say. And if you tell me what your problem is, I think I would be able to recommend that. So there's often just a handful of distributions that are relevant. So when you first come to Bayesian modeling, it's like, oh, well, there's like hundreds of distributions. Which one should I use? In reality, there's like 4 or 5 that are common, like the normal distribution, student t distribution, beta distribution, negative binomial if you have count data, and then a half normal. I mean, that's pretty much it. So if your data is, if you have a prior, right, then you probably don't have that much information that you can approximate some other ways. If it's a likelihood function, I would be surprised if it like looks really weird. And maybe if you have skew, right, then things could be a little bit more weird, but then there's a skew normal distribution. Or there's transforms that you can do on your data, right? So if you log transform your data, sometimes that makes it into a normal. If you have outliers, then use student t. So yeah, I think there are ways, but I don't recommend it. And I think there's a better solution. Cool. I think this is most of them, and we're right on time.
Excellent. Well fielded for the questions there. Thank you for scrolling through the chat and keeping on top of that. And thank you everyone for attending and sharing. So we have our next speaker in 3 hours time. That's Tariq Rashid talking on AI fairness and the state of the art, a very important topic. You've got the email that's got the links for today. So go back to that email for Tariq's Zoom call in 3 hours time. And then on Wednesday, we'll have myself speaking on higher performance Python, Marco Bonzanini talking on natural language processing, and some of the directors of NumFOCUS talking on why you benefit from contributing to open source. So please join us for the subsequent talks. Wednesdays will be emailed out shortly. And then for now, if you can thank Thomas on Twitter or LinkedIn and follow up with those other links with him, that'll be to your benefit. All right, thank you very much, everyone, for attending, and we'll see you at the next one. Thank you, Thomas.
Thank you, everybody. Had a great time.